Hello and welcome back. In this video, we'll be working through an example of computing a limit of a function of two variables. In the last video, we talked through some of the theoretical framework of how we're actually going to be able to do this. Remember, we didn't prove it in the video, but it can be proved, these particular limits. And then all of these rules about limits can also be proved, that these all have to hold. So what this means is that as long as we're talking about sums, differences, constant multiples, products, quotients, this one is so long as m is not equal to 0, right? M can't be equal to 0 here. Should make a note, m not equal to 0. If it is, then maybe this limit doesn't exist. So long as the function that we're dealing with can be made using combinations of these, and these as its base units, we can compute the limit by direct substitution. So that is, look, what we have here, we have x, y, and some constants, right? So x, y, and some constants. Here we have a x squared, but we have a limit law for a function being squared, so that's x squared. We have a limit law for products, so we can do this by direct substitution. We have a limit law for addition of two functions, and then we can examine this function. Well, it's a product of x and y. We know both of those limits, and then it's a square root of that, and we have a limit law for fractional powers. Remember, this is xy to the 1/2. So long as this isn't negative in here, we're fine. So this limit is just, so x is going to 2 and y is going to 8, so this will be 3 times 2 squared times 8 plus square root of 2 times 8. So that's what? 12 times 8, that's 96, right? Plus square root of 16, which is 4, and so we get 100 out. So the limit is, as we approach the point 28 in the domain, is 100, all the function values. So let me remind ourselves what this means in terms of the geometry. The function values approach 100 as we approach the point 28 from any path. No matter what path we take to the point 28, as long as we're in the domain, which is all of the xy plane. No, x and y have to be positive. As long as we're in the domain, as we approach 28 from any path in the domain, our function values approach 100. That's what this means, this calculation we just did. This is the consequence. Okay, so it's not too bad. If you want, you can stop the video here. If you're still wondering how exactly I got to just being able to do direct substitution from those basic functions and then the combining functions, I'm just going to run through what that actually looks like sort of formally here. Feel free to stop the video if you want, but if you'd like to see this, I do recommend it. So what those limit laws are really telling us is how we can move this limit. So I'm going to call this point xy. I'm going to call it p. I'm going to use that notation, and then p naught is the point 28. That's going to be a little bit helpful for me, just notation-wise, as I write this. So those rules for combining functions means here I have a product of 3, so I can do limit as p goes to p naught. So I'm going to split it up with the sum first. 3x squared y, right? We have the limit law for sums. So that means I can sort of, if you want to think about it like this, distribute the limit operator over the sum. That's what's going on there. And now I can analyze each one of those. I can distribute the limit operator over products. That's what one of the limit laws says as well, right? That was the product of two functions. This one I can distribute over products. Earlier we used we can distribute it over sums. And so this is going to be, we can do 3. If you've taken discrete with me, you can use induction to prove that you can do it for any number of any finite number of products. You start talking about infinity, again, if you've taken discrete with me or just any discrete class, you know, once you start messing with infinities, things can get a little bit wonky. So I can distribute this limit across the product. Here, one of the limit laws told me I can distribute it into fractional powers. Again, so long as we're not approaching a point that's going to make this negative in here or even 0, because then we might have to consider a fringe case. This might be a boundary point. We'll talk about those later. But in this case, since we're approaching 2.8, we're fine to bring in the limit. There's always some caveats, right? Of x. And then, you know what? Once I bring it in, I can distribute it over the product that's in there. So that's the idea, is I'm distributing this limit to every little piece. One last thing I'll do, is, just so I don't have to write an entire line here, is I'm doing limit as p approaches p naught of x squared. You know what? I'm going to change that. I'm going to bring the limit inside of the square. One of our limit laws says we can do that, and put it on the outside. Now we should have every piece together. Limit as p approaches p naught of a constant. Well, we had that constant rule, so that's 3. Limit as p approaches p naught of x, so we're approaching the point 2.8. Remember, sorry, I scrolled down too much. We're approaching the point 2.8, and so that base unit tells us this is just 2, and then square that times that one goes to 8. Over here, we'll get square root of that one. So that's one of our base units. That's 2. And here's another one of our base units. That's 8. And so then we get our 100 out. So that's really what's going on behind the scenes. If you stuck with me through this whole video, awesome. I'm so glad you watched through that, because I think it's always good to kind of peel back the walls and look at all the machinery that's going on underneath, right? Okay, that's it for this video. We'll start talking about continuity, and soon get into derivatives. That'll be really cool. All right, I'll see you there.